Number 1, use unison to find the parameters of the general ideal activity model combined with ideal gas law. So we're going to be storing everything in Excel. So we go back to the beaker and go to the fluid packages tab. So beaker, fluid packages, and select view. And here you'll see binary coefficients. The general Navier model, you can see the expression up here for tau, and you can see in the alpha expression, and you have AIJs, BIJs, CIJs, alpha 1, alpha 2. For almost everything that you'll do in this project, you'll only be dealing with AIJ, BIJ, and alpha 1. Everything else is 0. You have 3 components, so you have binary pairs, total of acetic acid, ether, acetic acid, water, and ether water. So you have 3 binary pairs, and if you recall, essentially, if you recall from your phase equilibria, we did in the class, but the alpha is essentially the tau in Chandler, and the A's are related by temperature to the J's in Chandler. In that class, I wrote you the exact connections. But if you recall, the J's are asymmetric. G component A, component B is different than G component B, component A. On the other hand, the taus were symmetric. So the AIs and the A's and the B's have to do with the G's. Okay, what it calls tau. The notation is pretty different. But so the A's and the B's are not symmetric, the alphas are symmetric. Sometimes you have A's, sometimes you don't. I believe you'll always be seeing B's. If I click here, I'll see the B's. And you'll see nothing under C's, or zeros, F's, or zeros, those G's, or zeros. Alpha 1, you'll always see values. And here you can see it's symmetric. 0.297, 0.297, 0.3, 0.3, 0.22, 0.22, okay?
What does that mean?
So the alphas are always going to be symmetric.
What does that mean?
If you look at the calculations for activity coefficient, you have both G, for example, you have both the parameter acetic acid, ether, and ether acetic acid. So if they are symmetric, they're the same value. If they are asymmetric, they're not. So when we talk about the parameters of the model, we're talking in this case about the AIJs, the BIJs, and the alpha 1 IJ. And you have a certain default parameters, and if I reset parameters, you always get this default parameter. Okay, so if I see the first one, but you can see I go back here. If I change something, okay, say okay. So I've changed something, becomes blue. If I want to get back to the original default parameter, just press reset parameter. And you'll get back to the original parameter. You go back to BIJ to see what you got it back. It goes back almost to the edge. Okay? Unison offers you 3 meaningful, let's say, parameters. The default are based on some experimental data and are supposed to be generally your best bet. But there are also molecular calculations, and you get the choices of unified VLE, unified LLE. VLE is supposed to be better for vapor-liquid equilibria, LLE for liquid-liquid equilibria. If I want to get this, I can choose to do all binary pairs. If I click all binary pairs, you can see the values changed. I did for the VLE all binary pairs. If I choose LLE, all binaries, you have that. Immiscible, you get some extreme values, you have total immiscibility, never use it in my lab. So, okay. But sometimes the default gives you the best results. Sometimes unified VLE, sometimes unified LLE. And in your project, you have 3 choices of parameters for every binary pair from Unisim, and you also have choice of parameters from Aspen Plus. Aspen Plus may offer from 1 to 4 choices. So for some of them, you will have 7 choices. 4 from Aspen Plus and 3 from Unisim. You need to choose which one is the best, which one you should use in your design. So how would you do that? You need to try to find experimental data. And obviously you have ethanol, and obviously you have water. You better find TXY diagrams, ethanol, water. So when you're looking at your database, you also have times when I'll ask you specifically for that. But start looking early for any TXY or PXY diagrams that involve components of your chosen reaction. Okay? Because you're going to be comparing it to experimental TXY diagrams and then choosing, okay, this set of parameters is better. And for what particular binary pair, it could be Unisim parameter set is better. For another one, it could be the Aspen is better, etc. Now, Unisim has an idiosyncrasy, which is also in classical high-speed. It presents parameters transposed. So what would be, let's say a B, ether, let's say ether acetic acid. Normally the first index is row, the second index is column, okay? So in Aspen and text you'll see A ether water, and you'll have a certain value. With the A ether water, in Unisim, you would have to look at ether in the column and water in the row. It's the opposite of what you would normally expect. So be aware of that. Also, what Unisim calls alpha 1, Aspen calls C. So that C is not the C of Aspen. As we will see in a minute, you will need for your project to be going back and forth between Unisim and Aspen. Unisim is going to be used for all your simulations, but you will need to get ternary diagrams that will guide your design of separations. And that you can only obtain in Aspen. So when you're going from Unisim to Aspen, you need to be translating the Unisim parameters to Aspen, and when you're going from Aspen to Unisim, vice versa. So I'll give you very clear instructions to make sure you know how to do it. So in this case, let's start with the default. I mean, if you know it, don't better, you start always with the default parameters or reset parameters to get back the default parameters. And by the way, yeah, if I put all the bits to 0, what have I done? And all the, yeah, if you have the A's and the B's as well.
Ideal?
Yeah, ideal picture, exactly.
Nice.
So if there is something that it doesn't have information, it will give you a warning and we'll set it for ideal picture. Okay, so I want to copy those parameters to Excel because we are going to be translating those parameters to Aspen. So I need to have those values. So let me start Excel. Let me go to Unisim, and if you click the upper corner, you highlight all of them. How about no music, guys? No whistling. Thank you. Control V, and actually I should have, let me undo that. Let's give some, actually let's put it down here. Yeah, let's put it down here, Control V. And these are what? These are the A parameters. So these are the B parameters, so these are Bij, and we need to know which are the components. And the ordering of the components that we have here are acidic, ether, water. So I'll go back, and I'll put an A, E, yeah, A. So I'll make it larger in a minute. W, let me make it larger. And of course, if it's the same component, that is meaningless, so there's nothing really there. It's supposed to be. And also, so this is A, B, and what? Okay. We should always have AIJs. You'll find AIJs for some binary pairs, absent from others. Here we can just say 0, 0, 0. Okay, and finally, we have the alpha 1. So to copy and paste, I should have slowed down there, sorry. Let me go back here. The easiest way to copy and paste, if you click the up, this triangle here, you select all of them. Yes?
I'm not getting the values and I'm not getting the top equation display. Is there anything that I didn't get?
What do you mean? You don't get the top equation displayed? You don't. You probably chose the wrong package. General NRTL, not NRTL. That was it, right? Yeah. Okay, let's go get also the alpha 1s. So again, I click right here, not where the cursor is. You see what? Click here. Right here.
Oh.
Yeah, I know it puts it here, but that's where I click. And then you select all of them. And then Control V on Excel. So Control copy after you select it, and Control V here. Okay. So those guys, Control copy, Control V, Control V. And I should have left an empty row. Let's click on one. Let's right click and insert a row. And we should say here Unisim default. So this is Unisim default. So these are the parameters for these three components that Unisim has as default. Okay, and let's save this file. file, save as, and we can call this, I don't know, problem 1. So that was what I asked you to do in problem 1, to find the parameters and report them, save them next time. All right, now let's go ahead. These are the parameters that we have and model the separation. Is everybody caught up or someone else more time? You okay? All right. So, exit this and return to simulation environment. So, we have two feed streams. One is acetic acid with ether, and it's 40 kilograms per hour total flow, mass flow, and it has 25 weight% acetic acid. So it's 30 ether and 10 acetic acid. So let's bring a material stream. Double click on it. Let's call it ether feed. And it is at 25 degrees C1 atmosphere. So fill in 25 and fill in 1 atmosphere. And let's go to composition. We have the composition is weight percent, not mole percent. So careful, the default is mole fraction. You need to change it to mass fraction. So go to basis and change mole fraction to mass fraction. Okay? So under composition, select mass fractions. And it's going to be 0.25 for acetic acid, and the rest of it, of course, 0.75 for ether. Click X, and now 0.25. Window pops up. I put 0.75 on the ether, and in this case there's an OK, so we click OK. So if there's an OK, a close, etc., you click that. If there isn't, you click the little X. So click OK. Okay? And go back to conditions, and we're given the total flow rate 40 kilograms per hour. So mass flow rate, careful, mass, not molar. Mass, not molar, 40. And that defines one feed stream.
Oh, shit.
And I know it might be 5 times there. All right. Okay. Adam, you can see it clearly now?
No, I think it is 0.25.
All right. Let's define the second stream. Make it a bit bigger first.
No problem.
So the second feed stream is going to be the water feed stream. So bring a second material stream. We can name it water. That is pure water at the same temperature and pressure. And the flow rate of this is going to be 60 kilograms per hour. So temperature 25, C, pressure 1 atmosphere.